Hey guys, we're going to do some more implicit differentiation in this video. So I wanted to do this video not just to get some more examples, but also to start explaining why we do certain things at certain times, particularly when it comes to notation. For notation reasons, and it depends on what kind of problem you're looking at sometimes, depends on what notation we're talking about. Something as simple as find the derivative could mean saying find f prime or saying find dy dx. And it all depends on what you need versus what you have. So in this section with implicit differentiation, the derivative is going to be dy dx. And we do this because we don't have y equals all by itself. If we had y equals, then we could just do direct differentiation and it wouldn't be a problem. But since we have two y's here, and they're both on different sides of the equation, I'm going to need to wiggle this around a bit. And I'm going to end up having to treat the derivative almost like it's a variable itself. Now I could use y prime instead. I could say that y prime is dy dx. And technically that is true. So why do I use dy dx instead of y prime? Well, part of it is personal preference, but the other part of it is that I already have y's in the problem. So having y and y prime in the same problem that I'm looking at can be kind of confusing. So instead, I use dy dx to make it just that little bit more obvious of what I'm looking at. So finding this lovely derivative using implicit differentiation, I'm going to find d dx of both sides of the equation. And on the whole of it, that's not that bad, especially the right side. There's only the one thing there, 5y. So using our power rule and our constant rule, I can say that d dx of 5y, well, that 5 can come out front, and I can take d dx of y, which is 5 times dy dx. No big deal. But the left side here, not nearly as nice. And the reason is that the power itself has y in it. So what I'm going to end up doing is the chain rule. And as we keep going and we keep learning more rules and more formulas, they're going to stack on top of each other. So having them that way will help. Now I'm going to treat my exponent here as my chain. So u, chain rule uses u, will be 2xy. So once again, this starts getting into notation. If I'm using dy dx, then when I need to use the chain rule or stacking other rules on top of it, I need to have more ways to help me differentiate one rule from the next rule. And part of how I do that personally is color coding. Having the blues and the greens in the same problem will help me differentiate, no pun intended, one part from another part and making sure I don't accidentally miss anything. So the chain rule says that I need the derivative of the outside times the derivative of the inside. So if my u is 2xy, then I'm going to end up doing the product rule to be able to find u prime, or du dx. So that would be, and I can push 2 out front. So the product rule says f prime g plus fg prime. So that would be 2 times 1 of x, and then that would be x, and then g prime in this case, du dx would be dy dx. So that would give me 2y plus 2x dy dx for that piece. So the derivative of my outside here, well, that's the product rule for the derivative of u, but I also have to take care of the derivative of the outside, which is the chain rule part. So I've got a derivative inside a derivative stacked on top of a derivative. This is why you use different notations and different colors and all these different things to help you keep things straight. So technically speaking, the chain rule says that I'm going to need to do the derivative of e to the u times u prime. But u prime itself is the product rule. So that's why I use different colors and different notations to help me keep track of what goes where when. Now the good news is the derivative of e to the x is just e to the x, so that's no big deal. So e to the 2xy times u prime, so that'd be 2y plus 2x dy dx. Okay? In my opinion, just this part, going from step 1 to step 2, can take a lot of time. Be careful. Go slowly. Don't skip any steps. Now that we have the derivative of each side, we want to solve for dy dx. So there's not much there on the right, but on the left, I can distribute that e to the 2x. So 2y e to the 2xy plus 2x e to the 2xy dy dx equals 5 dy dx. And then every term that has dy dx I want on the left. Every term that doesn't have dy dx I want on the right. And then I'm going to treat dy dx as a GCF. So that ends up doing this. Everything that's a dy dx on the left, everything that's not a dy dx on the right. Treat dy dx as if it is a GCF, which it is. And then I can divide. Just like that. The simplification part, after you get to this step, can be interesting. For example, I almost want to cancel out those 2's there and there, but since the 5 doesn't have it, I can't. Oops. So you got to be careful. Let's do another one. So this one actually says calculate y prime. Well, y prime is the same thing as saying dy dx. The first derivative of y with respect to x. It's the same thing, mathematically speaking. It's just the difference of notation. So why do we use different notations? To make it easier on ourselves, to help keep track, to help not skip anything. The basic idea is the same every time. We're going to take the derivative with respect to x for every term. So d dx, d dx, d dx, and d dx. I can immediately see that I'm going to have the product rule in this first one, and the rest look pretty simple of just the power rule. So we can go from here. So the product rule says f prime g plus f g prime. If I split it down the middle and I push that 4 out front, well, if this bit here is f and this bit here is g, then f prime will be 2x times g of y to the 7th plus f. G prime would be the power rule, 7y to the 6th, and then we have dy dx, because it is implicit differentiation. And all of that is for our first term. Notice I did it in a different color blue. Notice that I wrote out the product rule in one step at a time. I didn't try to simplify it. I didn't try to change it. I went directly one for one. F prime times g plus f times g prime. The simplification comes after. Make it as easy on yourself as possible as you go along. So the next term, we have the derivative with respect to x of negative 2x, which will just be negative 2. And the same thing for the next one, 5x to the 4, and then plus 4 times 3y squared and d dx. So we're dealing with y this time, dy dx. Now you may be wondering why I'm not doing that on the 2 and the 5x to the 4. Well, that's because technically I am. The difference is that instead of dy dx, it would be dx dx. Well, dx over dx is just 1, and 1 times anything vanishes. So technically it's there, but since it vanishes, we just don't write it. So now I'm going to start simplifying. So we have this lovely distribution of the 4 on the left, and we have a bit of 12 on the right. I do it this way to make as few mistakes as possible. So 7 times 4 is 28. I also make sure that it's written correctly. If I write it differently in the manner that I'm used to writing it, I make less mistakes. And that's part of being human and having habits. We like habits. Habits make it easier and faster. Okay? I can't see anything else I can simplify easily, so I'm going to take all the dy dx terms, put them on my left, all the non-dy dx terms on the right, and then I'll treat it like a GCF. So dy dx and 28 x squared y to the 6th, and I'll end up subtracting the 12y squared equals 5x to the 4th minus 8xy to the 7th plus 2. And then I will divide it out. Now, also technically, I did skip a step, but I can't skip too many steps in a row without messing myself up. All it takes is a missing negative, and you'll fall. And there we are. Now I found dy dx, which is the exact same thing as y prime with respect to x. Why do I use dy dx? Because it's easier to keep track of what I'm doing. Okay, let's do a hard one. Let's try to do the second derivative. And this is the equation for a circle. Before I can do anything, I have to find the first derivative. So, d dx of everything. And in this particular case, it's not that bad. So, d dx of 22x squared would be 22 times 2x plus 2y dy dx equals, well, the derivative of any constant is 0 every time. So 22 times 2 is 44, but I'm going to subtract it to the other side. So negative 44x, and then divide by 2y. So dy dx is negative 22x over y. Lovely. To be able to find the second derivative, you have to find the first derivative. Now here's where things get a little interesting, because the process is the same. The process will always be the same. The difference is when it comes to some of the simplification, and here's where notation can help you out. So, d dx of both sides, well, d dx of dy dx is, if you look at it just all by its lonesome, just this part, you'll see the two d's go together and the dx go together. So this is how they get that notation of d squared y over dx squared. Technically, this is what happens. The dx is squared both. But since it's easier to not write it with the parentheses, and we all know and do it the same way, we can write it this way, and the system says it's the same thing. So that's where that notation comes from, instead of y double prime. But once again, same thing. Now for the right side here, we're going to end up doing the quotient rule. We have a negative and we have a 22. I'm going to shove both of those out front to make it as easy on myself as possible. So I'm just dealing with the derivative of x over y. So the derivative quotient rule says f prime g minus fg prime over g squared. So just x over y. So if x is f and g is y, then f prime is 1, and g, that's y, minus f. G prime, well, we're doing implicit differentiation, so that's dy dx, over g squared, so that'd be y squared. There's the quotient rule. Okay, so now we can get a little bit more interesting. I put that negative 22 out front, and I'm still not making it not out front yet. In fact, I don't like this. It's weird and annoying, so I'm not going to do that. What I'll do instead is this. And it's strictly to make it easier on myself. Technically, it's the same thing. Math doesn't see a difference. We see a difference because we have habits. So I just want to simplify this numerator as much as I can before I start thinking about simplifying with my denominator. And here's the other part. Dy dx all by itself, we know what that is. We just found it. Dy dx is negative 22x over y. We just found that. So now we can keep simplifying. So how do you add fractions? Well, you got to have a common denominator. The only denominator there is the y itself, that way. So I'm going to multiply my first y by y over y. So I'll get y squared over y. Negative times the negative is a positive 22x squared over y. And I have y squared plus 22x squared over y divided by that y squared, which is the same thing as saying multiply by 1 over y squared, which makes this lovely denominator here y cubed. And you may think we stop, but this is where color coding comes in. All of that was my medium blue. And I look up and I see my darker blue. This lovely negative 22 drops. So I can distribute that all the way across to finish. Or I could, but I remember something. What do I remember? I remember what I started with. And what I started with told me, point blank, that 22x squared plus y squared equals 10. Well, what did I just find? 22x squared plus y squared. I can rewrite that as 10 over y cubed. There we have. So my second derivative is negative 220 over y cubed. So you end up having two sets of substitution here. The dy dx, which we found first, and then the original in the green. Be very careful and don't skip steps. Okay, let's do one more. We want to find the first derivative of this lovely thing. And then we want to find the slope of the curve at the point 16,4. Well, the slope of the curve is the derivative at that specific point. So in finding our first derivative, that's going to aid us in the second part anyway, so that's always nice. But first we need to find the first derivative. So I'm looking at this and I'm going to end up doing d dx of every term. And each of these terms, especially these first two, that's the product rule, isn't it? So I'm going to end up doing f prime g plus fg prime of each one of those. Once again, color coding is my friend. I'm going to do the first in blue, and I'll do the second one in green. So, if this is f and this is g for my first product rule here, then f prime is just 1, and then g would be y 7/2, I'm not changing that, plus f. G prime, well, that's the power rule, so 7/2 times y, and I go down a power, so that would be 5/2, and then dy dx. So that all by itself is the derivative of that first term. And once again, I did not try to change the problem. I did not try to simplify at the same time. I did spot for spot f prime g plus f g prime. I didn't do anything else. So I didn't try to switch it around. I didn't try to multiply. That comes later. So now let's do the same thing for our next term. The first will be the f, the second will be the g. So f prime, so that would be 3/2 x and then go down a power. And technically I would do dx dx, but that's 1, and 1 times anything goes away, so I'm not worried about that. So f prime times g, which is y, plus f g prime, well, y all by itself would go to 1, and then we would have dy dx. And lastly, I didn't mean to do that, but it works, the derivative of any constant is 0. So that's nice. It's only after we do this initial set of find the derivative of each piece do we start the simplification process. So distributing and combining terms, moving dy dx to one side, and then getting rid of it all. So let us start this lovely process. Okay. So I'm also going to write things correctly. So this time, my second term here, I put the coefficient out front. X comes first, y comes second, and then the dy dx. Same thing with the next one. X comes first, y second. Okay. All dy dx terms are already on the left, but I still need to move the non-dy dx terms to the right and treat it as a GCF. So dy dx, 7/2 xy to the 5/2 plus x to the 3/2 equals negative y to the 7/2 minus 3/2 x to the 1/2 y. Careful of your negatives. Careful of your negatives. And divide. So dy dx negative y 7/2 minus 3/2 x to the 1/2 y all over 7/2 xy to the 5/2 plus x to the 3/2. So there's the first derivative. Woo-hoo! That took me a second, but I did it. Double check. Find the slope of the curve at 16,4. So every time I see an x, I'm going to put 16. Every time I see a y, I'm going to put 4. And I'm going to use a different color. Or at least, I'll mark where the next one is. There, that'll be nice. Color coding is extremely helpful. Use it to your advantage. So, and be careful of those lovely negatives. x16 to the 1/2 times 4. 7/2, 16, 4 to the 5/2 plus 16 to the 3/2. And you can either use your calculator, but that can be iffy depending on how well you know how to type this in. But if you remember some key things, 4 to the 7/2 power is the same thing as saying the square root of 4 to the 7th power. Well, the square root of 4 is 2. 2 to the 7th power is much easier to figure out than 4 to the 7th square root. Mathematically, they're the same thing, but I can figure out the first one in my head way faster than I can figure out the second one. And use it to your advantage. Okay, so there we go. And 3/2 times 16, 24, 7/2 times 16 times 32, All 16 divided by 2 is 4. 7 times 4 is 28. 28 times 32. No, that's wrong. 16 divided by 2 is 8. 7 times 8 is 56. There we go. 56 times 32 is 1792 plus 64. There we go. Much better. And then divide. Make it nice and pretty. So I am thinking 19 over 232. The moral of the story is to go slowly, one step at a time. Don't overwhelm yourself. One step at a time. Use your resources and use what you know. Try color coding. I didn't discover it in math class, but once I did, it works so well that I haven't stopped using it since. So give it a try. Use different notations to help you to keep things straight. Don't skip any steps. And if you need help, ask for it. Use your resources. Your tutors, your instructor, your textbook, YouTube, Google, all of those things are there to help you. Use them to your advantage.